Hello class 12th, we are discussing the topic electromagnetic induction, and in this topic we have read about Faraday's law and Lenz rule. We will discuss today an amazing fact that if a conducting rod is moving in magnetic field in such a way that this rod behaves like a cell, it becomes polarized. How it happens? We will discuss today, and the EMF developed in this rod, that potential difference across the ends of the rod, is called motional EMF. Today we will learn about it. What is motional EMF? As per its name, the EMF developed in a conductor due to its motion in magnetic field, that is called motional EMF. How it is derived? Suppose this is the uniform magnetic field and its direction is perpendicular to the plane of paper inward, like this. Now this B is uniform and a rod of length L, suppose this is the rod and it is of length L, it is moving with the velocity V in this direction. What is the angle between V and B? Look, this is V and this is B, 90 degree. If this rod is made up of conductor and if it is moving in the magnetic field as I have shown here, then along with the rod, conductors has large number of free electrons as well as the positive ions from which the electrons are free. Then what will happen? We have read that if a charge moves in magnetic field, then Lorentz force acts on it. How the Lorentz force is decided? By using Fleming's left hand rule. This finger in the magnetic field direction, this finger motion of positive charge, and this finger force, Lorentz force. Look here that if the magnetic field is like this and if this is the finger denoting the motion of positive charge, then what will be the force on that? Upward. What I mean to say that if this is the direction of force represented by thumb is upward for the positive charge, then what will be the direction of force for the negative charge? Downward. So we can say that all the free electrons which are moving along with the rod in the left to right direction, they will experience the Lorentz force in the downward direction and positive upward. So since electrons are free to move, they are free electrons, so here accumulation at this end, suppose this end is P, will become negative and equally positive will be the other end from this, its name is O, from these atoms from which the electrons are detached and accumulated here. And look, this is the potential difference developed across the ends of the rod. So how it is developed? Because the magnetic force, that is Lorentz force, acting on the electron, I will write here only the magnitude of it. If I write here, then it will be E V cross B sin theta. Since V cross B sin theta, theta is 90, we can write here this Fm equal to EVB sin theta. Since theta is 90 degree angle between velocity and magnetic field, so it will be EVB. What happens? The electrons accumulate at this end P, then electric field is developed across the length L of the rod and directed from O to P. What will happen? Initially the Fm is very large, and when this large number of electrons, they are accumulated at P, then electron has tendency to move in the direction opposite to the electric field. So what happens? On these electrons in the rod, electrical force acts in the direction from P to O. So, electrical force which is given by the Fe, I am representing here, it is EE, it is acting upward, and Fm is acting downward. A steady state, in the steady state, when this electrical force from P to O becomes same as magnetic force, that is called steady state, then what can we write here? This EVB equal to EE, what electric field we get here? VB. And as per the electric field, its magnitude, we know electric field is potential gradient. So, magnitude, electric field is negative potential gradient, we have taken magnitude here. So, we can write here, that is this potential difference across the ends of the rod, it is shown by capital V upon L equal to VB. So, this V equal to BVL. Look here, all these three L, V and B, they are perpendicular, and this is called motional EMF. It is also represented by this EMF E. So, in this way, whenever the rod is moving, it is in this direction I have shown. So, whenever the rod is moving perpendicular to the magnetic field, maximum EMF is generated and the velocity is V, this length of the rod is L. If you join this rod with a conducting wire, you can also show that induced current will be produced. Now, the circuit is complete. So, the current will begin to flow from this direction to this direction and like this. So, you can see that how much EMF is produced, and this is called motional EMF because it is produced due to motion of the rod in the magnetic field. Now, if the rod is sliding on a rectangular conducting frame in the perpendicular magnetic field, then what happens and how will you find the expression for motional EMF and how Faraday's law is derived? Suppose this is the conducting frame, and again like the previous case, we have taken the magnetic field, this cross magnetic field uniform. At this frame, without friction, the rod is supposed to be moving with the constant velocity in this direction. So, after some time, suppose it will cover the distance dx, this end, suppose this is P and this is O. So, this OP end of the rod will cover certain distance dx, and in the time dt, the dx distance is covered and it reaches at the position O dash P dash. What happens? Here you know phi is B dot A magnetic flux, and that is BA cos theta. Look here, magnetic field is downward, and suppose this L length of the rod, area is L into dx, you can write, and initially when the rod was at OP, this much was the area, and when the rod moves dx distance in the time dt, then the increase in area. So, how can you write here for theta? Theta is the angle between area vector and magnetic field. Magnetic field is downward, and you can suppose this area vector is also downward. So, what is theta? 0. So, the flux maximum will be BA, and as per definition, all the field lines are passing through the area. So, this is flux. Due to the motion of the rod, what will be the change in flux. So how will you find what will be the change in flux? B is constant, you can write here this B, and here you can write this dA, change in area. What is change in area? Initially it was from this point, suppose M point to P. So this one was the area, and after dt time the area is from M to P dash and this whole. So what is change in area? You can find here this change in area is L dx. If we can write this L dx, so what will be delta phi upon delta t? What will you do here? This will be B L and here dx by dt. That is, the rod is moving and it has covered the dx distance in the time dt. What is dx by dt? Velocity. So you can write here this is BLV. And what is delta phi upon delta t? Rate of change of magnetic flux linked with the closed circuit. This is called EMF. So we can derive the motional EMF in this way also. Look here that what will be the direction of current? So if you use this, how will you say that the current direction will be anti-clockwise? How can you say? Look how the EMF is derived. This is BLV. And how will you find that Faraday's law that has been proved here is showing that if the circuit is complete, then direction of induced current, this is direction of induced current. How will you find? How can you show? Look here that if the rod is moving with the constant velocity, then since the whole rod is moving in the magnetic field, then induced current direction, as previous case we have seen, this end P will become negative and this end will become positive. So this rod behaves like the cell. You know, cell is having this terminal positive and this terminal negative, and if the cell's ends are connected with the conducting wire, then the direction of current is like this. And what is within cell? Within cell from negative to positive terminal. So as in the previous case and here also, the direction of induced current will be from P to O, and in the outer circuit this P to O, this is the cell, and outer circuit like this. We can also explain how the Faraday's law, they are explainable here. Look that if area increases, then EMF opposes its cause of production. Cause of production is increase in area, then what should be the EMF produced? EMF produced will be opposite. You know what is EMF? If you take the Lenz rule, then EMF is minus d phi by dt. Then how will you find this minus sign? Explains Lenz rule that if phi increases, then what will be d phi? This d phi will be positive. Therefore, EMF will be negative. And look here that this is the P and negative and O is positive. Here this is the cell, from this to this end. This total OP rod has, it is equivalent to a cell of EMF BLV. We can also prove that if in a circuit the uniform magnetic field is there, but the whole circuit is moving within the magnetic field, what will be the induced EMF? We can understand by supposing that these two ends, they are moving perpendicular to the magnetic field with the same velocity v, the whole circuit is moving. So, we can also assume this. Look here, these two ends will become like, we can show here that they will become like the two cells. So, how can you show it here? I can show it here. Look, this is the one cell and this is the other cell. So, you can show here that in the complete, within the uniform magnetic field, if the whole circuit moves with the constant velocity, then I induced will be 0. Why? Because this is positive direction of same EMF, this is positive terminal of same EMF, and if the two cells are connected like this, what will be the current? 0. And we have proved that by Faraday law, if the whole circuit is moving completely within the magnetic field, there will be no flux change, because all the field lines will pass through it. Their number will remain same. If flux change will not be there, then no induced EMF will be net, and no net induced EMF, that is no induced current. So, in these two cases, we have seen that all B, V and L, they all are perpendicular. So, maximum EMF, that is motional EMF, is maximum when a conducting rod is made to move in the magnetic field perpendicular to the magnetic field, and all three B, L, V, they all are perpendicular. Now, if I take a typical example that all B, L, V are not mutually perpendicular, then what will happen? Suppose this is the rod. I take this rod is of length L. Okay. Now, this is the magnetic field, and if this rod is, suppose it is moving with this velocity v, then L is the length of the rod, and this is the angle between magnetic field and the length, and this is the angle, any of the value you can find. Suppose this is the angle alpha. Okay. Now, as we have seen previously, we have seen that motional EMF was produced due to motion of the conductor in the uniform magnetic field, and it was maximum when all these three were perpendicular, then motional EMF was B, L, V, its product. What will happen here? V and B are not perpendicular. Then what will you find here? Like previous case, look here that V and B are not perpendicular, motion of the free electrons will be downward direction, you know, you can find in this with the same explanation. So, this, and here you can write here this Fm, that is magnetic force acting on the free electrons, and what will become this? Look here, how will you find how the magnetic force will act? What will be the motional EMF due to that polarity across its ends? So, look here that this Fm, magnetic force acting on the free electrons, and the free electrons will accumulate at the end, that will become negative and the other end will become positive. So, what will happen? How will you find the polarity across this end? You know that if V and B are given in this way, then you have to use this right hand rule, that from V towards B, curling of the finger from V towards B, then whatever is the thumb, its thumb is denoting across the end, that end becomes positive. So, what will happen here? If the rod is moving like this, then this end, you know, from V to B, you can find. How will you find? Using this V to B direction. So, this is Fm you will find EVB, and as like previous case, that this electrical force will be opposite to the magnetic force, so this will be minus Fm. We have taken earlier. What is electrical force? EE, and this is Fm minus EVB. Here not only EVB, look here, this V and B, what will you write? This EV cross B, because EVB can be written only when angle between V and B is 90 degrees, sin 90 will be 1. What is here? This is V, this is B. So how can you find that if this is V? So from V to B you have used this one. So look here, this E equal to minus EVB, V cross B I can write here because of the vector notation, and these are the vectors. So E will be cancelled, and we are getting here, this is minus V cross B. This is the electric field. Now what will happen if this is the electric field? So what will you do? That to find the potential difference across the ends of the rod, what will be the V cross B vector's direction? You know, as per the right hand rule, what will be the V cross B vector's direction? So look here, that V and B, it is given here, and the V cross B vector from V to B we have shown like this. This is V cross B, and what this vector is making angle with the length of the rod, that is, suppose length is L, then how will you write here what will the potential difference? You know, electric field is negative potential gradient, that is dV by dl minus dV by dl. So what can you put here? This implies that this minus dV by dl, you can write dl on the other side. So this will become minus V cross B into dl. This small potential difference, this is for the smaller length, we can integrate for the whole length. So integrating, what will you get here? This minus minus will be cancelled. So this minus dV will become integration of dV, and here this is V cross B, and this will be integration dl. So finally you will get this V equal to V cross B vector and dot L. Look here, in this expression, this is the general expression. With this general expression, any type of question can be solved, whether B, L, V, they are not mutually perpendicular. Any of the angle will be given, you can find. What you have to do? First, you have to find the V cross B vector using right hand thumb rule. Then that vector's direction and what is the angle between that vector and length vector. Then you will find dot product of that, and finally will be EMF across the ends. How will you use? I am going to give such examples that show that how motional EMF can be obtained in various cases. Look, suppose in the first example there is a uniform magnetic field, and if the rod is moving in this direction, we have seen that this end will become negative and this end will become positive, and motional EMF will become BVL. Why? Because all three, length, magnetic field and velocity, they all are perpendicular. You know, V cross B, you know how to find V cross B? Look, my this thumb and fingers, V to B. The fingers of right hand should move from V towards B. Look, the thumb, so this end will become positive, this will become negative, and this is V cross B and L. How V cross B? Look, Motional EMF, you have just now seen that this is V cross B dot L. Look here, V cross B vector, this V, this B, so V cross B vector is here in this direction, V to B, so this is the thumb. What is thumb? Thumb is denoting the cross product of V and B, so this is thumb and length. How were they? Parallel. So what will become? This V cross B into this is dot product dot L. So what will you write here? VBL cos theta. What is theta? VB and L both are parallel. So this is VBL, hence it is written. In another case, suppose this is the direction of magnetic field. Now you look, if you take the rod and if this rod is of length L and it is moving in this direction, no EMF will be produced, 0. Why? You can find what will be V cross B. They are in the same direction. V cross B is VB sin theta, sin 0 is 0. So by observing you can find what is motional EMF. Another case, suppose this is the magnetic field and this is the rod and it is moving, suppose in this direction, this is V and this is the length L. Okay. Now how will you find that in this case? How can you say that motional EMF will be produced or not? Look here, length, this is length and this B, they are parallel. What I mean to say that if motional EMF is BVL, then it will be BVL if all these three are mutually perpendicular, and out of these three, if any of the two are parallel, then there will be no EMF. How can I write here no EMF? How will you justify that no EMF? Look, again you find V, this is B. Look, what will be the V cross B? So this will be the direction of V cross B. Look my thumb, V cross B will be downward, and what is L in this direction? So if the general relation you have written when they are not mutually perpendicular, then this is V cross B dot L. This V cross B is, as I have shown, like this, and this thumb is denoting V cross B vector, length and V cross B vector, they are perpendicular, so it will become VBL cos 90. So it will become 0. So how many cases I have given? Another case, suppose this is the magnetic field and this rod is moving in this direction. Look here, this is L. Same V and B, you can find they are parallel. So either V or B or L or B, like this you have shown. This is velocity in this direction, here this direction, or whatever may be the case. If any of the two vectors are parallel, then no EMF will be induced. A very interesting example. Finally, I am going to tell you that suppose there is a magnetic field which is uniform and a rod is of the semicircular shape, is shown like this. It is here in the magnetic field like this. What happens? This rod moves with the velocity V in the uniform magnetic field B. What you have to assume here, that this rod is of semicircular shape, but you have to take the length of rod as its diameter. Suppose this is the distance r, then what will be the length of the rod? You will write length equal to 2r. So the displacement length you have to assume, then how will you find that what will be the EMF induced in this rod? Look, this is V, this is B. How will you find what will be the, suppose this end is, I am writing here M and this is P. First you decide what will be the polarity. Look, the velocity vector and this is magnetic field downward. So look my fingers from upward to this direction downward. Look, upward to magnetic field is inward. So look my finger. Where is the thumb? Towards the end M. Look. So M end will be positive and this P end will be negative. So what can you say? That motional EMF will be, you know, BLV. What will you write here? BL is 2R into V. So in this way you have to solve the questions. Whatever may be the direction given, you have to find, you have to use this general relation. This is E equal to V cross B dot L. So in any of the cases, we have seen that if the uniform magnetic field is given like this and the rod is moving on a frame which is frictionless and it is moving with the velocity V, we have seen due to the Faraday's law that E equal to minus d phi by dt equal to this B V L. We have seen EMF, motional EMF BVL, and minus sign is Lenz rule. It is explaining the Lenz rule. Lenz rule also explains the energy conservation. So look here, suppose this rod has the resistance R, then what will be the current induced in the rod? How can you find the direction of induced current? As I told you that this rod is moving towards V in the uniform magnetic field B. So this end will become negative and this end will become positive. We have seen direction of current will be like this, from positive to negative. This end, suppose PM, this end will become the cell of terminal P positive and M negative like this. What will be I? Induced current, E upon R. So what will you write here? This is BVL upon R. So in this way you can also find what will be the magnitude and direction of induced current in any of the circuit, and if the rod moves in the magnetic field, how the EMF is produced. That is called motional EMF due to motion of the conductor in the magnetic field, and in what direction it is produced, the current is produced in the circuit. I hope you must have enjoyed it. Thank you.